This conference will now be recorded.
Hello everyone. Effective atomic number, that will be the first topic, and then we'll be discussing the related problems, and after finishing it there will be very important topic which is metal carbonyl complexes. There are so many important aspects that are related to these metal carbonyl complexes, and based on these questions are also very common and important also. And if after that time permits, then we'll discuss the important applications of coordination compounds. So effective atomic number, in short we call it E, A and N. So this concept, it was first proposed by Chiswick, and the purpose behind it is to explain the stability of the complex. So suppose any coordination compound is given, and after calculation of EAN, there is some specific rules based on which you can understand, that is just looking at the EN value, whether it is stable coordination compound or not. So that is the purpose to behind this concept. Okay, that is to explain the stability of the complex. An ion with central metal atom possessing EAN equal to next inert gas, that will be more stable. Now next inert gas means, suppose the coordination compound in which there is obviously a metal, and the metal is from any specific period. Okay, so it may be third period, fourth period or fifth period, depending on from which transition series you have taken the metal. First transition series mean it may be third period, fourth period, fourth period, fifth period and sixth period. Fine. Now if it is third period, that means first transition series, suppose you have nickel, cobalt, copper, this type of metals, then obviously you have to consider the last noble gas, and the last noble gas before that, that will be there is some specific noble gas obviously. So for each transition series you have to check the corresponding noble gas. So if it is following that inert gas configuration, it will be stable, and if it is not, then it will not be stable. So we can get some idea about the stability, though exceptions are also there. It is not that always if it is not matching with the inert gas configuration, it will not be stable, but that is very rare. Okay, the central metal atom of the complex generally belongs to third, fourth, fifth period of the T block. Okay, and the noble gases, it will be actually fourth, fifth and sixth. Okay, not third, fourth, fifth and sixth, because the first there is only if you consider the first period, there is only helium and hydrogen. Then the second period, there is lithium, then carbon, oxygen, there is no D block, right? So D block, it is basically starting from fourth period. Okay, now the central metal of the that is a noble gas that belongs to these periods, that is third, fourth and sixth, they are basically krypton, xenon and radon. So they will be considered when we will calculate the effective atomic number. Okay, so there is for each period, specific period, there is a particular noble gas present at the last group, that is group 18. Okay, so obviously more than one cannot exist, right? So depending on which metal is actually present, it will be krypton, that is atomic number is 36, then 54, and radon, which is 86. Now suppose if you are considering the metal complex which is from this first transition series, then you have to check whether it is matching with 36 at EAN or not. If it is from the second transition series, now you have to check whether it is matching with 54 or not, and if it is from third transition series, then it must match with 86 value. Okay, now the purpose behind it is that, suppose if you consider only metal, there is a specific atomic number. Suppose just take nickel, it has atomic number 28, but when some ligands are surrounding it, now some more electrons are also should be counted surrounding the metal. That means after addition of these ligands, the new electrons that are added, this combined number, if you see that it is matching with the inert gas configuration, that is inert gas atomic number, that means it will be stable. It can be defined as the resultant number of electrons present in the metal atom or ion, depending on whether the metal atom it is having zero oxidation state, or ion means it will have some specific oxidation state, 2 plus 3 plus whatever, after accepting electron from the donor atoms of the ligands. So if you consider only metal, there is a specific atomic number, and then when you consider the oxidation state, it may be 0. If it is 0, there is no effect, but if it is 2 plus or 3 plus, then you have to subtract those number of electrons, and then you have to consider the addition of those electrons that are coming from ligands. So how to calculate it? Very easy. First you have to consider the atomic number of the metal. Next you have to consider the number of electron lost in the particular oxidation state formation. Suppose if it is nickel, it has atomic number 28, but if it is having oxidation state 2 plus, then you have to subtract 2 electron. So that is there is a negative sign. Then plus number of electrons gained from the donor atoms. Now the donor atoms that will be attached with nickel, suppose there are total 4 chloride. So these are the donor atoms. So each chloride is donating two electrons each. So that electrons also you have to consider. So there is a plus. Okay. Now if we take specific example, here we have taken the example of K3FeCN6. Now you don't have to consider this counter ion, just focus on this part. Fine. So if you remove this K3, there will be negative charge outside the coordination sphere, that is outside the third bracket, it will be 3 minus, right? And 6 ion ligand and 3 negative charge extra, that means oxidation state is plus 3. So oxidation state is plus 3, atomic number of iron is 26, that is atomic number Z is 26. So EAN calculation, what you will do? First you will write the atomic number, then subtract the number of electrons that are lost in the ion formation. So here 3 electrons lost, so that is why minus 3. And there are total 6 cyano ligand, and each cyano is carrying, that is 2 electrons are donated by each cyano. So that is why 6 into 2. So it will be 12 electrons that will be added. So ultimately it is 26 minus 3, that is 23 plus 12, it is 35. That means iron, which is in the first transition series. So now we will consider this number for the first transition series, but it is not equal to 36. So that is the reason we cannot say that it will be very stable. There will be a tendency to accept electron so that it can achieve the configuration 36. So to attain 36 electronic configuration, the iron in this compound, it will have a tendency to accept an electron. That means it will act as oxidizing agent, because the tendency to accept electron is nothing but oxidizing agent. So see, if this complex is given and if it is asked, account for the oxidizing that is oxidizing property of this metal ion in this on the basis of effective atomic number. So these will be the reason. Okay. So sometimes question may be given at a particular compound is given, and you have to it will be simply mentioned that find the EAN. Sometimes it may be also mentioned that whether is it following the EAN rule or not. That means whether it is equal to the inert gas atomic number or not. That we have to check. So question may be in different style. Okay. If it is directly asking that find the EAN, it is very flat question, fine. But indirectly also it can be whether it is following EAN or whether it is stable or not. Predict that based on EAN. So there are different ways question may be asked. Okay. So any doubt how to calculate EAN? Now we'll discuss some problems based on this concept. So here the problem is saying that metal carbonyls having formula MCOX. The value of X is not given. So it is metal carbonyl complex. What metal? That is also not directly mentioned. Here the number of carbonyl unit, that is the number of X basically, coordinated to metal M are formed by these three metals. Now effective atomic number of each metal is given 36. So it is already mentioned that all of them are following 36, that is EAN. So based on this information, you have to find the value of X. So obviously the value of X will not be same for all these three. It will be different because the atomic number is different. Okay. So suppose first take iron in place of this, that is just follow this formula, but instead of writing M, we have written Fe. So if EAN is 36, then that must be equal to 26 iron. Oxidation state is 0, so you don't have to subtract any electron. And for each CO, it is 2 electrons, so 2 into X. So from this equation, you can find out the value of 2X. 2X is 10. That means X is 5. So the formula for iron carbonyl will be FeCO5. Similarly, suppose if it is chromium, now chromium is having atomic number 24, so now it will be 24 plus 2X. Now this complex also oxidation state 0, because carbonyl metal complexes, if it is having only carbonyl, remember it is always 0 oxidation state because CO is neutral. So if it is 36, then it will be 12, so X is 6. Okay, and if it is NiCO4, now for nickel it will be 28, so it will be 28 plus 2X equal to 36. Now total number that is 2X will be equal to 8, so X is equal to 4. So see, the formula is NiCO4, for chromium CO6, for iron CO5. Fine. Any doubt? Which of the following does not obey EAN rule? That means it is asking which of them it will not have the corresponding inert gas configuration for the respective period. Though here all the metals that you have all are from first transition series, that is iron, second one is also iron, then Mn and vanadium. Fine. The K4 Fe6 in the previous slide, what we have done, we have seen already K3 Fe6. But now in K4, negative charge outside the sphere is 4 minus. That means oxidation state is now 2. So for this EAN will be, for iron it is 26. Oxidation state plus 2, so we will deduct minus 2. And 6 into 2, that means 12. So what value you are getting is 24 here, 24 and 12 is 36. So that means it is following. Okay. Then for FeCO5, FeCO5 again 26, but now oxidation state is 0. So you don't have to subtract anything. For each carbonyl it is 2, so it is 10. Again we are getting 36. Now the Mn complex. Now this is something different. It is having 2 metal center. Okay. Now 2 metal center, it is actually bimetallic complex. Fine. So for this complex, first you have to understand the structure. Each Mn is containing CO, 5 CO. Now what you will do, though this is symmetrical structure, so only for one half basically you have to do the calculation. So suppose as if you are dividing it like this. Now for Mn, atomic number is 25, right? How many CO are there total? One more is there, 5, because per Mn it will be 5 CO, because here in this structure we do not have any bridging ligand. If bridging ligand is present, that is different case, but as we do not have, so So it will be 5 into 2, that means 10. But here remember one thing, whenever you have bimetallic complex and if there is metal-metal bond, in this case you have metal-metal bond, though it is always not necessary that bimetallic complex means metal-metal bond will be there. No, that may not. In this case it is bimetallic and there is 2 electrons present. So when you are basically dividing this structure, so this for this mm bond, that is metal-metal bond, 1 electron also you have to consider. So that is why +1. So ultimately we are getting 36 again. So this is also following. So the last one must be the correct answer because we have to find which one is not obeying, right? Then the last one, vanadium having atomic number 23, oxidation state is 0 because it is carbonyl complex, and 5 into 2, that means 10. So see, this is not at all following EAN rule. That means it will have a tendency to accept electron so that it can achieve 36. So the last one will be the correct answer because it is not obeying EAN rule because it is not equal to the value 36 because all are from first addition series. So the inert gas that you will consider is for krypton. Okay, any doubt?
No, ma'am.
Now in this complex we have how many total? 6 complexes. Fine. Nickel, iron, Zn, Ni, and again iron in 6. So all these are from first transition series, only Pt which is from third transition series. Okay, so when it is first transition series, basically you have to consider the number 36, right? But remember, look, just consider the first slide. If it is the third transition series, now Rn, that is atomic number 86, you have to consider. Fine. Which of the above complexes have the same effective atomic number? So here we have some groups, that is option A there are 3 complexes, option B there are 3, then again in C 3 and in D there are 2 complexes. Fine. Now total 6 are there. Okay. Now the first one, that is NiCO4. Ni is having atomic number 28. There are no other ligands, so it is having oxidation state 0, and for each CO there is 2, so 4 into 2 it is 8. And we have to find what EAN is same. It is not in, you don't have to see whether it is matching with 36 or any other inert gas number. That is not our focus. Our focus here is just to check in which case we are having same. So that you will have all these complexes in a single option. So this is 36. Now for the next one, iron, outside 4 minus, so this is +2. So 26 minus 2 for each cyano 2, so it is 12. So this is also 36. Now see, you can find a trick here, that is 1 and 2 both are same. Now in which option 1 and 2 both are present? It is option C and option B. So D and A you can easily cancel out, and among B and C one of them will be correct. So now after doing this, you can either check 3 or you can also check directly 6 because 2 simultaneously cannot be correct. Any one of them should be correct, either 6 or 3. So look at 3 now. Zn 4 ammonia 2 plus. Now ammonia is neutral, so oxidation state of Zn is 2. Atomic number for Zn 30, then -2, and for each ammonia it is 2, so 2 into 4, that means 8. So ultimately -2, 28 plus 8 is 36. So 3 is also same, that means this option must be correct. 1, 2, 3 same, right? And why not the other one correct? Let's check. Nickel 2 minus, negative charge outside, 4 cyano ligand, so oxidation state is +2. Atomic number 28, then -2, then 4 into 2, 8. Okay. So it is 34. Please, you can also check whether I'm doing it correct or not. 28 minus 2, 26, and plus 8, 34. Then we have PT. Fine. Now PT, suppose if you normally it is difficult to remember all these atomic number, right? So suppose just in case if you have forget the atomic number of PT, what you can do? Just simply follow the valence electron. That is PT, it is in the same line of nickel, that is same group of nickel, then palladium, then platinum. So for nickel, try to remember how many valence electron. It is 3d8 4s2, that means 10 electron. So same should also be for PT. So instead of writing atomic number Z, if you write 10, this is also another way you can do EAN calculation. So what I am doing, I have written valence electron, not atomic number. Okay, and oxidation state is 4 plus, so minus 4. For each ammonia it is 2, so 12. Now 10 minus 4, 6. 6 and 12. What we are getting? 6 and 12, it is 18. Fine. Now 18 means it is actually 36. But as you have not considered directly the atomic number, so that is why you are getting the value in this way. And 18 is also atomic number of one inert gas, which is argon. But if you follow the actual rule, if you can remember the atomic number, it is actually 78, then minus 4, then plus 12. So minus 4 plus it is 74, plus 12, and it is 86. Now as PT is from third transition series and the corresponding inert gas Rn, so Rn is having 86 atomic number. So see whether you follow this rule or this one, actually you are getting the same result. So from both you can understand it is following EA. So if you are considering, if you in case if you can't remember the exact atomic number, just don't worry, follow the valence number of electron instead of writing Z. But in that case you will obviously not get this high number, you will get the number which is equal to argon. Fine. So here also basically it is following EA, but what we have to do, we have to just check effective atomic number same or not. And what about 6? The 6 is iron CN6 3 minus, oxidation state plus 3. So 26 minus 3 plus 12. So it is 23 plus 12. So this is also not equal to 36. So 1 to 6, that is also not correct option. Option B is the correct option. Fine. So if you get this type of question, don't just blindly find out all the EAN for all these 6. Just check that it is for this, it is true that after finding calculation, doing, that is completing the 3 calculation, we are able to choose the correct option. But it may not be so always, but still you have to be alert whether if you don't have to do the calculation of all these complexes, obviously that will be time saving. Okay. The effective atomic number of cobalt tetra-carbonyl complex, it is given 35. Now it does not attain stability by which of these process? Effective atomic number given 35. It does not attain stability by which of these process? Now the EAN that should be that is for stability, the number that is expected is 36. That means it should gain 1 more electron. Now the first option is saying that oxidation of this complex. Now oxidation of this complex means what? It will now lose electron. But if it is so, then it is not equal to 36. So this cannot be correct. Then reduction of this cobalt tetracarbonyl. Now this is possible because, why it is possible? Because reduction means what? Acceptance of electron. And if you want to move from 35 to 36, you have to accept one more electron. So this is possible. And the third one is saying dimerization of this. Now this is also correct, because when there is dimerization, you have now metal-metal bond. That is cobalt-cobalt bond. That means one more electron will increase per metal. So this is also possible. And the last option is saying that both B and C. That means this should be correct. So EAN is 35. It will acquire stability when it will become 36. So this is possible if it gains electron either by reduction, and if it is forming dimerization, that means CO4, CO4, I am writing in the left hand side. So if there is dimerization, then also it is possible. So that is why this is the correct option. Okay. Any doubt? Both the problems clear?
No, ma'am. Clear, ma'am.
So after finishing EAN, that is effective atomic number, next topic is metal carbonyl complexes. Now first we'll see what kind of bonding is present in this type of complexes. And the most important question is why we are discussing this particular type of complex separately. Because there are so many types of ligands, right? Chloride, bromide, there is any halide, then water ligand, ammonia ligand, cyanoligand, all these are common. But why we are discussing only metal carbonyl? That means MCOX in general, if I write. So metal carbonyl complexes, first of all, they are very common and they are also very stable also. So because of this, their stability, we'll find many examples of metal carbonyl complexes, and their applications are also very high. They can also be used as catalyst. Now, why they are so stable? If you want to know their reason for stability, basically you have to understand the bonding. So here we have a special kind of bonding that is present, which is not present in other type of complexes, and that is making these complexes so unique, so different from others. So these are the transition metal complexes of carbon monoxide ligand, and metal is attached with CO. And remember, when we are talking about carbon monoxide ligand, it is always making bond through carbon. It is not like this, that carbon is this side and oxygen is towards metal. This is completely wrong. This is the correct way of writing the structure. That is, metal is interacting through carbon of carbonyl, not through oxygen. So at a first glance, you may seem that oxygen should be the atom with which it should interact with metal because it has lone pair. No, that is not the case. So when you will see the bonding, basically, then you will be able to understand why it is making bond only through carbon, not through oxygen. So it is containing metal carbon bond. These are formed by most of the transition metals. That is, this type of carbonyl complexes, that is very common for all types of metals. And simple, well-defined structures are there. The first homoleptic carbonyl complex that was reported by Mond is this one. Remember, homoleptic, this definition we have already discussed during the discussion of ligand type. Homoleptic means the complexes, but you have only one type of ligand. So here you can understand you have only one type of ligand, only CO. You do not have any other type of ligand. So that is why it is homoleptic complex. And the first metal carbonyl complex reported by Mond is nickel tetracarbonyl. These metallic carbonyls are widely studied because of their industrial importance, as I have said, catalytic properties, and also the ability to release carbon monoxide. So this is also very unique. That is, they can be used as a source of carbon monoxide. So they can release carbon monoxide. So these, because of these reasons, they are very, that is, widely studied by scientists. Now this particular ligand, it is different from other ligands in many respects. Unlike the alkyl ligands, the carbonyl ligand is unsaturated. If you consider alkyl ligand, suppose methyl ligand, though methyl ligand we have not seen yet, but that is very common in if you consider organometallic chemistry. Fine. So instead of any alkyl ligand, the carbonyl ligand is basically unsaturated. That means pi bond is present. Not in all the any ligand you will find pi bond, but in this case pi bond is present. For example, water or ammonia, there is no pi bond, but carbonyl there is pi bond. So that is the reason it not only forms ligand to, that is ligand to sigma donation. Now ligand to sigma donation means ligand is donating electron towards metal. Normally we know this, right? And this is possible because it can donate from ligand to metal. But remember, the unique thing is that it can also accept electron in its pi star orbital from d pi metal orbital. Now after giving electron towards metal, metal had different d orbital. So metal first what it will do, it will accept electron in its vacant d orbital. But after that, suppose metal is also having some field orbital. Now these field orbitals, it can donate electron to the pi star orbital of L. Why we are saying pi star? Because pi star is anti-bonding ligand, and anti-bonding ligand, anti-bonding orbital, if it is vacant, then it can easily accept electron from the field orbital of metal. So this occurs here, and that is the reason they are also known as that is CO ligands are known as pi acidic ligand. Your acidic nature means what? Acceptance of electron. So it is accepting electron from metal through pi bond formation. So there is basically pi star. Pi star means this is also pi bond. So D of M and P of CO, it is making pi bond, because pi bond is, we know that pi bond is formed between two P, that is common, but between D and P, that is also possible. This kind of bonding, that is also possible. D pi P pi bond. So that is actually occurring here, and as now carbon monoxide is accepting electron from metal, so that is why it is also known as pi acidic ligand. So suppose 4 or 3 ligands are given and it is asked among these which one is pi acidic ligand. So any of this ligand, if it is CO, you can consider it as the correct answer. The other differences lies in the fact that CO is a soft ligand compared to the other common sigma ligand or pi basic ligand. Just take the example of water. When metal interacts with water, it is basically interacting through oxygen, and oxygen is highly electronegative, so it will have some hard nature, and in this case it is interacting through carbon, not oxygen. Now carbon is not so electronegative like oxygen, so it has some soft kind of nature. So because of this water ligand, there is interaction with oxygen. If it is alkoxide ligand, suppose MEO, methoxy, then also interaction is through oxygen. So all these are basically hard ligand because here the atom through which interaction is occurring, that is highly electronegative. But CO is not such, it is soft ligand. So that is another unique feature. So now this point, that is first there is sigma bond formation, then pi bond formation, and the direction of electron donation, first from ligand to metal, then the reverse direction, metal to ligand. This point we will elaborate more, so that we can understand what kind of bonding is actually present. So in this slide you will see this bonding in metal carbonyl, that we'll try to understand. Metal carbonyl bonding interaction, it comprises two types of bond. The first one is CO2 metal sigma donation. CO2 metal sigma donation, look at the first picture. Here CO, it is donating electron from its field orbital towards the vacant D of metal. Okay. And the second type is metal to CO pi back donation. So this word is used back because already sigma bond is there and donation is already there from metal ligand to metal. But now the reverse process is occurring, so that is it is back donation. Now see this metal d orbital, it is filled. Here this one is filled, but now the filled orbital is towards metal. And this is pi star ligand. So as it is pi star, so see orbitals are not, that is, they are away from each other because there is phase sign is not matching. So that is according to definition of anti-bonding. So that is why the orbitals are it is drawn like this. And now the metal is donating electron from field towards the vacant pi star. So this pi star is vacant. So this is metal to CO pi donation, because now the bond is sidewise overlap. So this is pi bond, but this is head-on overlap. This is sigma bond. Okay. So in metal carbonyls, electrons density moves from ligand to metal through sigma bonding, the first process, and then from metal to ligand through pi bonding. So this type of effect, that is both direction, there is interaction going on. So this type of effect is known as synergistic effect. And this accounts for strong metal CO bond in metal carbonyl complexes. So this is the reason why metal carbonyl complexes are so stable, because here both way electron donation is taking place. A and B. Suppose A is also giving B, B is also giving A. That means here both direction electron donation is going on. So that is the reason here stability of this AB bond, or in our case it is MC bond, metal carbon bond, that is very strong. Now this observation, there are some evidence also. So this observation, it is in agreement with the fact that low valent transition metal centers, that is transition metal atoms, they can only form metal carbonyl complexes. So you will always see that whenever you will have any metal carbonyl complexes, it is mostly metal zero. Even if it is not metal zero, suppose some other ligands are also associated, then also you will see that is, even if oxidation state is present, it will be very low oxidation state, maximum +2, or +1 is better obviously than +2. That means it is not very electron deficient. If it is 0, obviously not deficient. If it is +1, slightly deficient. Then if it is +2, deficiency is increased. But if it is low valent, then only it can form metal carbonyl. The reason is because after taking electron from ligand, metal also giving electron. So it must not be very deficient. Otherwise, back donation will not be possible. The direct effect of pi back donation, there is also that is observation, which is in supporting this process. So what is observation? It is observed on the metal C bond distance that becomes shorter as compared to that of normal metal carbon single bond. So there is, suppose only sigma donation is occurring. Suppose the second process is not occurring. So what you will have? You will have only metal carbon single bond like this, M, C, and then there is a CO bond, right? So this is single bond. But if metal is also giving electron, now it will have some double bond nature. And whenever there is double bond nature, obviously that means bond order is increasing. So bond length will decrease. So metal C bond, now it will be shorter. So if it is shorter than normal single metal C bond, that is also the proof that pi back donation is going on. Okay. So here if you look at this picture, this is only sigma bond, but suppose if there is also pi bond occurring, that means metal is also donating electron. Now one of this bond, that is, if you simply draw carbonyl, there is basically triple bond. Okay, different ways you can draw carbon monoxide molecule. So this is one of the way by which you can draw it. And here if you draw it like this, there will be positive charge over oxygen. But the important thing here is that if it is metal carbon single bond, Now the stretching frequency, and when this is stretching frequency of carbon monoxide. This is also stretching frequency of carbon monoxide. Remember, whenever bond order is increased, here bond order is 3, here bond order is 2. That means if you consider stretching frequency of CO, then obviously it is higher when pi back donation is not present, but it is lower when pi back donation is present. So more is the back bonding, lower will be the stretching frequency of CO. So with respect to free CO, suppose there is no metal carbon, free carbon monoxide molecule, then the stretching frequency value 2143 centimeter inverse. But if you have metal carbonyl complex, now there is a significant shift in the value, because now because of this pi back bonding, stretching frequency will decrease because of this back bonding. But another kind of stretching frequency you can also have, which is stretching frequency for metal carbon bond. So if you consider metal carbon bond, then stretching frequency in the first case and stretching frequency in the second case, in which case it will be high when bond order is high. Here see, bond order is high between metal and carbon. I am not talking about the bond between carbon and oxygen, that is already done. Now I am talking about bond between M and C. So in the first case you have single bond character, in the second case you have double bond character. So when bond order is increasing, so obviously now stretching frequency will be high. So if you are considering stretching frequency of CO, obviously it will be decreasing, but for metal carbon it will be reverse. Okay. Now look at this example. Here we have taken some complexes. First look at the complexes. All are carbonyl complexes. But what is the difference? TiCO6 2 minus. That means here oxidation state of titanium is 2 minus. That means it is highly electron rich. Then VCO6 outside coordination sphere single negative charge. So it is -1 oxidation state. Then chromium CO6, it is 0 oxidation state. This is +1, this is +2. So as you are moving from titanium to vanadium to chromium to Mn to Fe, basically oxidation state first 2 minus, then -1. That means oxidation state is going towards more positive value. So the metal center is becoming more electron deficient, right? Now look at this stretching frequency value for CO. So higher is the electron density over metal. Obviously, back donation will be very good. And when back donation is very good, that means stretching frequency will be very low, because back bonding is inversely related to stretching frequency of CO. When back bonding is very high, stretching frequency is very low for CO. So here back bonding will be maximum because the metal center is highly electron rich. But as you are moving towards right hand side, it is becoming deficient. From -2, then -1, then 0, then +1, then +2. That means now the metal is not so electron rich that it can make proper pi back donation. So that is why look at this value, gradually it is increasing, right? 2204. Now 2204, it is almost very close to free CO value. So here stretching frequency is very low. That means just from the value of stretching frequency, suppose some complexes are given 4 to 5 and the corresponding stretching frequency for CO is also given, and it is asked that in which case, that is from this try to understand in which case pi back bonding is a maximum. So you can easily understand why the value is minimum, pi back donation is maximum. Another way also you can get question, suppose all these complexes will be given and these values will not be given. So just look at the complex and you have to find out in which case back donation is maximum and stretching frequency will be minimum. So that is also possible. Another question can also be framed in that way. And if you consider stretching of metal carbon bond, so increasing metal double bond character as you are moving towards left hand side towards titanium, because when pi back donation is very good, metal carbon double bond character is generated. So here increasing metal carbon bonding towards left hand side, but decreasing metal carbon bonding towards right hand side. So two different thing, don't be confused. One is CO bonding, when it is very back donation is very good, CO bond order is decreased, so that is why stretching frequency is also low. But if you consider metal carbon bond, now from single bond character you are getting double bond character like this. So all the discussion in this particular slide, because this is very important, if the basic idea is clear, then any type of question you can answer. Any doubt? Should I repeat any part? Now after bonding, next we'll see classification of metal carbons. That is different. This classification, it can be done based on number of metal atoms present. That is how many metal atoms are present. And this is one type of classification that we'll do here. After that we'll see another type of classification also, which will be whether there is bridging CO present or not, metal carbon present or not, based on this. So first we'll see the most simplest, that is mononuclear carbonyl. So you will have only one metal. So these compounds contain only one metal atom, and they are very simple, right? NiCO4, it is 4 coordinated tetrahedral, then FeCO5, trigonal bipyramidal, that is TBP geometry. Then CrCO6, it is octahedral. Okay. So these are the examples, mononuclear carbonyl. And comparatively not so simple. Now if it is polynuclear, so metal carbonyls where 2 or more metal atoms are present. That means mono means just one metal. But if it is more than one metal, suppose 2, 3 or 4, so metal carbonyls containing 2 or more metal atoms, they will be now called polynuclear carbonyl. And some examples here we have, see, 2 metals, but the category is homonuclear. That means all the metals will be same. So CO2, then 8 carbon monoxide, Mn2, 10 carbon monoxide, Fe3, 12 carbon monoxide. But heteronuclear is also possible, though that is comparatively less common. Now see, we have two different types of metal. Manganese cobalt, 9 carbonyl. Manganese rhenium, 10 carbonyl. Rhenium is just below Mn, and that is not just below MnTc and then Re. That means in the same group of manganese. So here we have some pictures. So here Fe3, and see how many CO? 4. Then this Fe, it is attached to CCO, 3 CO. This is also 3 CO, and here 2 bridging. That means 8. And here we have 4. So this is basically Fe3CO12. See, 3 iron and total number of carbonyl 12. But all these iron, they are not having same environment, because if you consider this iron, it is not having any bridging CO. It is just having 4 CO. But these two, they are having 3 carbon monoxide without bridging and 2 carbon monoxide with bridging. Then the next one, this one is M. How many CO? Each metal 4 CO. And total how many metal? The general formula is M3. 4 into 3, that means total 12. Now this metal, it may be ruthenium or osmium. So see here in the first box, we have complexes of iron, ruthenium, osmium. And iron, ruthenium, osmium, they are from same group. First iron, just below it ruthenium, then osmium. So they are complexes, that is these two are forming same type of complex, but iron, it is different, comparatively different with it. And then Mn2CO10. So see here we do not have any bridging CO, and each manganese is attached to 5CO. Okay, and we also have metal-metal bond. Now this one is heteronuclear. Rhenium attached to how many CO? 1, 2, 3, 4, 5. This one is also 1, 2, 3, 4, 5. That means MnReCO10. This is the picture of this heteronuclear complex. So this is one kind of classification. Next classification, it is based on the structure. The structure of binuclear metal carbonyl involve either metal-metal bond or bridging CO. Because when you have binuclear, they must be attached, that is two units must be attached to each other. Now this attachment is maybe two types. It may be through metal-metal bonding that you have seen in the last two pictures. See, there is metal-metal bonding between two manganese or one manganese, one rhenium. This is one possibility. Another possibility is maybe there is no metal-metal bond, but how the units are attached? Through bridging. And another possibility may also be that both metal-metal bond as well as bridging carbonyl, both are present. Fine. So either metal-metal bond or bridging CO or both. The carbonyl ligands that are attached to only one metal atom, obviously they are not bridging. They are known as terminal carbonyl. But those are attached to two or more than two. That is also possible simultaneously. Now they will be called bridging because they are basically helping to attach two sides, right? So now it is attached to minimum two. It may be more than one, two, but minimum two must be there so that you can call it bridging. Now, depending upon the structures, metal carbonyls, now it will be classified as CA, non-bridged metal carbon. That means no bridging is there. Now, when no bridging, these metal carbonyls do not contain any bridging carbonyl ligand. Now, they may be two types. Non-bridged metal carbonyl containing only terminal carbonyl. Another is non-bridged metal carbonyls containing terminal carbonyls and metal-metal bonds. So see, non-bridged, why we are seeing, it is true that metal-metal bond is present, but bridging ligand CO is not present. So that is why we are calling it non-bridged. So this is the example. These are very simple mononuclear carbonyl complexes, but this is basically Mn2CO10. And each metal is attached with 5. Okay, so non-bridge metal carbonyls containing terminal carbonyls and metal-metal bonds. So here we have only terminal carbonyls and metal-metal bonds. Bridged carbonyl. These metal carbonyls contain one or more bridging carbonyl ligand. That is why the name is so, along with terminal carbonyl. That is two types of carbonyl will be there. Metal bonds may be present or not. So here we have the structure Fe2CO9. Name is diiron nonacarbonyl. It contains 3 bridging CO, 6 terminal CO. So this is the picture here. See, 3 CO present as bridging, 6 terminal CO, but you do not have any metal-metal bond. So metal bonds, as here it is mentioned, it may be present or may not be present. So this is the case where it is not present. Now another example, dicobalto octacarbonyl. CO2, 8 carbon. Now 2 isomers are possible. One isomer, there is metal-metal bond, and another one, there is no metal-metal bond. Sorry, no bridging CO. That is I'm trying to say. In both cases, metal-metal bond is present. So the one has a metal-metal bond between the two CO, and the other also having bridging CO. So in the first one, you have only terminal. So suppose I am writing terminal because you T for terminal, okay? But in the second case, you have bridging as well as terminal. So this can exist in both these isomer, but remember from the sign of equilibrium you can understand if it is structure 1, if it is structure 2, mainly structure 2 will be the predominating. That is, if suppose in any question if it is not mentioned specifically which structure, then by default you can consider the second one because this is most predominating. That is why the arrow is longer towards the second structure. So any doubt in this classification? Problem we will discuss in the next class, that is based on this metal carbonyl topic. So any doubt regarding any slide in today's class? So we are ending the session here as there is no doubt. Thank you for listening.